Hello students, welcome back to my chemistry class. Today I am going to explain you about the compounds with incongruent melting point. Phase rule already explained for you. In that phase rule, we have seen one component system, two component system, condensed system, and incongruent system we have seen. Silver lead system completed, zinc magnesium. Now we are going to explain you about the sodium chloride and the water. So phase rule. It was first presented by Gibbs in 1875. Very useful to understand the effect of the intensive variables such as temperature, pressure, concentration, or equilibrium. This equilibrium is between different phases as well as different chemical constituents. So it was presented by Gibbs in 1874 in order to understand the temperature pressure effect on the different phases that are in the equilibrium for different chemical constituents. It is used to deduce the F. So previously F is equal to 0 invariant system, F is equal to 1 monovariant system, divariant system, trivariant system. Explain. What is the variance? Variance we have seen monovariance, divariance. So reduced phase rule also we have seen. When the equilibrium between any number of phases is influenced only by temperature and pressure and concentration, but not influenced by gravity or electrical magnetic forces or by surface action, then the number of degrees of freedom of the system, it is related to the components phases by this equation, that is phase rule. F plus P is equal to C plus 2. So here the condition is it is influenced by temperature and pressure concentration, but it shouldn't get influenced by the gravitational force, magnetic forces. Okay, then the number of components. Then this rule can be applied. F plus P is equal to C plus 2. F is the degrees of freedom, P is the number of phases, C is the components, okay, plus 2 variables, that is temperature and the pressure. Now we'll see the reduced phase rule. Phase rule at constant temperature. There are three invariant variables: temperature, pressure, composition, concentration or composition. If any one variable is kept constant, then that is a reduced phase rule. Here phase rule at constant pressure. Condensed system, it is based at the condensed phase systems, you get the reduced phase rule. So phase rule at constant temperature, condensed system, you'll be seeing at the constant pressure, the phase rule at the constant pressure. So condensed system, it has no gases. Silver lead system you have seen. So condensed systems have no gas phase when their properties are insensitive to the changes of the pressure, which are favorable. Only fewer variable needs to be specified. It results therefore constant pressure and F is equal to, or F plus P is equal to C plus 1. This is the reduced equation, or F is equal to C minus P plus 1. So this is the condensed phase rule. It is not applicable to the condensed system which is subjected to high pressure. The one which are at constant pressure or low pressure, then only this rule can be applied. Okay, so this rule is useful in the material sciences. This rule is useful in the material sciences. So phase rule, that is a normal phase rule for one component system, and for the condensed system, the reduced phase rule we have seen. Now we'll see the terminology. What is the terminology? So terminology used, I told you F is equal to C plus F is equal to, here F plus P is equal to C plus 2. or F plus P is equal to C plus 1. So for that, wherever you see you are having F, P, C. F is the degrees of freedom, P is the phases, C is the components. So what is a phase? It is defined as homogeneous, physically distinct part of a system having all physical chemical properties throughout. It is same throughout the system. A system which is containing homogeneous mixture. A system where here homogeneous mixture. So homogeneous and physically distinct part. Mechanically it is separable. That is nothing but a phase. For example, I told you previously, again, system it is having liquid water, then that is only one phase. System it is having liquid water and water vapor. One is the liquid and the other one is gas. It is two-phase system. A system it is having liquid water, water vapor and solid ice. Here liquid water is liquid system, liquid phase. Water vapor is the gaseous phase. Solid ice is the solid phase. So it is three-phase system. Any pure substance, solid, liquid or gas that made up of one chemical species, then that is as one phase. So oxygen, benzene, ice creams, all these come under one phase system. What is a component? The term component, it is defined as the least number of independent chemical constituents in terms of which composition of every phase can be expressed by means of chemical equation. The chemical constituents of a system of a phase is nothing but component. So the chemical components in a phase and in a system is nothing but a component. Water system has three phases: ice, water, water vapor. Ice is the solid phase, water is the liquid phase, water vapor, it is nothing but the gaseous phase. But the composition is the same, H2O. So it is one component system. Similarly, sulfur has four phases: rhombic sulfur, monoclinic sulfur, liquid sulfur, sulfur vapor, composition. Here it is S. So how many? Four phases are there, but only the composition is only one. So therefore, it is one component system. Sulfur system is also one component system. All the phases in one component system, which are expressed only by one chemical individual. They are expressed by one chemical. Now we'll take a saturated solution of NaCl in contact with excess of solid NaCl has two phases. Saturated solution of NaCl in contact with excess of solid NaCl. You can see two phases. The composition of both the phases can be expressed in terms of two chemical individual, NaCl and water. Saturated solution. So NaCl salt you'll be having, NaCl salt, and at the same time H2O water. So water is, NaCl is dissolved in water. So this is the salt and that is the, so after that you'll be getting the saturated solution. But the components here you can see NaCl and H2. The composition of the phases can be expressed in two chemical individual, NaCl, H2. And saturated solution of the NaCl in water in contact with excess of solid NaCl. It is a two component system. Similarly, you take calcium carbonate, solid. This calcium carbonate solid, this one it decomposes to calcium oxide and carbon dioxide gas. So here you're having solid phase and the gaseous phase. But the components, three, you can see three. It has three phases, but the composition of the phase can be expressed in terms of two of three chemical substances in equilibrium. Hence it is two component system. Now degrees of freedom. Degrees of freedom, it is denoted by F. It is defined as the least number of variable factors of a system which can be specified so that the remaining variables are fixed automatically and the system is completely defined. So the independent variables are degrees of freedom. In a simple way, I'm telling degrees of freedom, F. It is nothing but the independent variables are degrees of freedom. Are the degrees of freedom. Independent variables are nothing but degrees of freedom. Okay. So monovariant system will be having if F is equal to 1, that is monovariant system. Water, you get F is equal to 1. So pressure and temperature are the two variables. So these are independent. Pressure, temperature are independent variables. They are not interdependent. They are independent. And when you change, they change independently without altering the equilibrium of the phases. So thus the other one, it is fixed automatically. Hence the system has 1 degree monovariant or univariant. So here the system has two variables, pressure, temperature. It is having two variable. See, pressure, temperature. So these are variable components. These are independent variable components. As they change, the equilibrium of the phases will not get affected. That is degrees of freedom. Now we'll see F is equal to 1 for monovariant system. Now what is a bivariant system? F will be equal to 2. For a pure gas, PV is equal to RT. If P and T values are specified, there can be there can have only one definite value of V, or that volume is fixed automatically. Thus it has 2 degrees of freedom and the system is bivariant system. You have understood, I think. So PV is equal to RT. P and T values specified. So P and T values are specified. There can be only one definite value of V, or that volume is fixed automatically. Thus it has degrees of freedom and the system is bivariant system. Now, a mixture of two or more gases is completely defined only when P, T and C are specified. So it is a trivariant system. So it is defined only by P, T and C. If P and T specified and the third variable, that is composition, can be varied. Since it is necessary to specify 3 variables to define the system completely, it has 3 degrees, that is trivariant. Non-variant, F is equal to 0. F is equal to 0, that is non-variant system. So for ice, water vapor you take. So F. In this system, the 3 phases coexist at the freezing point of water. Since the freezing point temperature has a definite value, freezing temperature has definite value, the vapor pressure of the water has also fixed value. Since both the variables are already fixed, the system is defined automatically in the 3, and there can be no need to specify any variable. Here, no variable is required to specify. So that system has no degrees of freedom and it is non-variant system. Now, we'll see all the revision is completed. Now we'll see the compounds with the incongruent melting point. So what is phase rule? What is a reduced phase rule? What is F? What is P? What is C? We have seen with examples. Now coming to the actual class, today's class, compounds with incongruent melting point. Water NaCl will take. So that is the best example for the incongruent melting point system. The compound which undergoes decomposition by formation of another solid is said to have incongruent melting point. The compound which undergoes decomposition by formation of another solid, it is said to have incongruent melting point. So the phase diagram of the solution of NaCl water system. Your dashed lines are the tie lines that indicate the composition of coexisting phases. Coexisting phases. NaCl represents the dry crystal, NaCl, and NaCl H2O indicates the dihydrate system. This type of diagram, it is typical for salt and water interactions. It is given here, stable. Okay, so solid, liquid, and here you get NaCl. So four different system: NaCl, H2O, one phase you get in this diagram. So for NaCl, H2O system, incongruent system, you get four phases. NaCl, 2H2O is one phase. Only NaCl is one, and ice is another one, and total solution is one. Ice is one, NaCl H2 is one, only NaCl is one, and ice, only ice, the solution. Only ice, only NaCl, NaCl H2O, and the total solution is one phase. Totally you'll be getting four phases. I'm repeating, the compound which undergoes decomposition by formation of another solid is said to have incongruent melting point. For that, the example is water NaCl system. Now, we'll study in detail this water NaCl system. As I told you, the compound undergoes decomposition by formation of another solid is said to have incongruent melting point. The system in which the compound formed by combination of two components and decompose when heated by giving a new solid phase. The system in which the compounds are formed by the combination of two components. System in which the compounds formed by combination of two components. They decompose when heated and give a new solid phase and solution of the solid with different composition from the original solid. Such type of compounds have incongruent melting points. Okay, NaCl and water is the example. Now, two components combine to form the solid compound with incongruent melting point, in which decomposes before reacting its melting point. NaCl and water system is such type of system. It exhibits four phases: NaCl H2O, NaCl, ice, solution. Now the phase diagram is given below. Explaining this one, I'm going to explain you in detail the incongruent melting point. Here you're having here the saturated solution. Here I told you four phases: ice, NaCl H2O, total liquid, NaCl solid. Okay, total liquid, ice with that liquid, again NaCl H2O with that unsaturated solution. This total unsaturated solution one phase, ice plus saturated solution another phase, NaCl H2O is another solution, and NaCl solid with saturated solution is fourth phase. Okay. Now each curve, what is F will calculate and I'll explain. You are having here on Y coordinate you are having temperature. X coordinate you are having the composition of NaCl. And pressure is kept constant. This is the reduced system. Pressure is kept constant. So composition on x-axis, temperature on the y-axis. So it is low temperature below 0 degrees. This is the composition. Now we'll take the curves. Each curve I'm going to explain. A, O, B, O, again BC, BG, and this is CF. Looking onto the diagram, we'll see how this incongruent system changes its phases and what are the degrees of freedom. First, OA curve we'll see. OA curve. In this OA curve, that is the water freezing point curve, because during that OA curve, you will be getting ice. So water freezing curve you call it as water freezing curve. AO or OA. There water gets freezed out and you will be getting ice. So water freezing point curve we call it. So we'll look on to the curves and thereby we'll see how the phases and areas and the points, how the degrees of freedom is varying. Water freezing point is 0 degrees. Water freezing point is 0 degrees. From A to O, water freezing point it is decreasing. See here, it is 0 degrees. It is going to minus values. So it is getting decreased. Why it is happening? Because you are adding NaCl along the curve you can see. So from 0 degrees, the freezing curve it's going down. The freezing point is decreasing. Why it is happening? Because you are adding NaCl along the curve and the two phases are in equilibrium. Ice is in equilibrium with the solution. Ice is in equilibrium with the solution. In this, along this curve, ice is in equilibrium with unsaturated solution. So how many phases you can see? Two phases. Ice, it is the solid phase, and unsaturated solution is the liquid phase. So P is equal to 2. And composition H2O is one composition, ice, and NaCl is another component, another one. So the C is equal to 2. F is equal to C minus P plus 1. Our formula F is equal to C minus P plus 1. So F is equal to C is 2, P is 2 plus 1. 2 minus 2 plus 1. So F is 1. So along the curve, degrees of freedom is 1. And here along the curve, the system is univariant. Now we'll go for the OB curve. OB curve. So along this OB curve, NaCl H2O solubility curve. OB curve. OB curve. This is the NaCl H2O solubility curve we call. From O to B, solubility of NaCl H2O, it is increasing. From O to B, the solubility is increasing as the temperature from O to B is increasing. From minus value, it is going to 0. So the temperature is increasing along this curve. Two phases are in equilibrium. So what is the two phases? NaCl H2O. It is in equilibrium with the solution. NaCl H2O. It is in equilibrium with solution. So you will be getting two. You will be getting the solid as well as the solution. The phases are 2 and components are NaCl is 1 and H2O is another. So along this curve, you are having P is equal to 2, C is equal to 2. So F is equal to C minus P plus 1. F is equal to 2 minus 2 plus 1. Therefore, F is equal to 1. System is univariant system. So I have seen the freezing curve of ice OA and the solubility curve OB for sodium chloride we have seen. So ice freezing curve is OA and NaCl solubility curve is OB. Now we'll see BC. what is BC? Here, AO I have come, again from here, OB. So freezing point decreased along AO. Again, the solubility increased as the temperature is increasing from OB. Now we'll see BC. That is the solubility curve again. BC is also the solubility curve of NaCl. At point B, NaCl H2O changes into NaCl solid. NaCl solid along this curve, BC curve, temperature increasing. Here, this is the solubility curve. NaCl changes into the NaCl solid, solution changing into the solid. Along this curve, two phases are in equilibrium. NaCl is in equilibrium with solution. NaCl solid is in equilibrium with solution. This is NaCl solid is in equilibrium with solution. So phases are two, solid and liquid. C composition. NaCl H2O. Components are 2. F is equal to C minus P plus 1. F is equal to 2 minus 2 plus 1. F is equal to 1. System is univariant along BC curve. This curve indicates the solubility of NaCl is almost constant with increasing temperature. The solubility is constant with increasing temperature. This curve indicates solubility of NaCl. It is almost constant with increasing temperature. Now we'll see point. What is the point O? What is the point O? So this eutectic point or cryohydric point. You call this point O as cryohydric point or eutectic point. At this point O, three phases are in equilibrium. At this point O, the three phases are in equilibrium. Ice is in equilibrium with NaCl H2O. This NaCl H2O is in equilibrium with the solution. So at this point, the solution, ice and NaCl H2O, all these three are in equilibrium. 1, 2, 3 are in equilibrium at point O. So number of phases are 3. The number of phases you can get 3. 1. Okay. So 3 phases you'll be getting. And composition is NaCl and H2O. F is equal to C minus P plus 1. F is equal to 2 minus 3 plus 1. F is equal to 0. At point O, eutectic point or cryohydric point, the system is invariant system. Now, at point B, we'll see what is happening at point B. Then we can go on for the areas. First, incongruent melting point. B point is called as the incongruent melting point. The compound undergoes the composition to give another solid is having incongruent melting point. As I have explained in the starting, the compound undergoing the composition to give another solid is having incongruent melting point. NaCl H2O solid, NaCl H2O solid at point 0.15 degrees. Here, this point, the temperature is 0.15 degrees centigrade. It gives rise to NaCl plus solution. It is giving NaCl and the solution. At this temperature, NaCl H2O changes into solid, it is changing into NaCl solid. NaCl H2O, it is changing into NaCl solid plus solution. So a solid is coming out. Okay. At this point, three phases are in equilibrium. At this point, three phases are in equilibrium. So phases are three. 1, 2, 3. So P is 3. C is equal to 2. C is equal to 2. F is equal to C minus P plus 1. F is equal to 2 minus 3 plus 1. F is equal to 0. System is invariant system. System is invariant system. Now we'll see the areas. Coming to the areas, in the area A, O, B, C, above 3 is only one phase, that is solution. A, O, B, C. Above there is only one phase, solution phase. So I'm explaining you about the areas. 4 areas are there. Okay. So one area already calculated above, and OB calculated. Again the BC is calculated. The BG we have seen, and the point O we have seen. Now the areas I'm telling you, any area you take, here the area, in the area A, O, B, C, only one phase is there, that is the solution phase. P is equal to 1, only one phase. C is equal to 2. C is equal to 2. Okay, only one phase. Compositions are 2. Sodium chloride solution. Sodium chloride solution. In this sodium chloride solution, we'll be having NaCl plus H2O. So the components, what you can tell? It is 2. The components are 2. C is equal to 2. So therefore, F is equal to C minus P plus 1. F is equal to 2 minus 1 plus 1. F is equal to 2. It is bivariant system. So in this area, you will be getting bivariant system. I'm repeating. Along OA curve, it is water freezing point curve. So it is 0 degrees. From 0 degrees A to O, it is decreasing as NaCl is added. So two phases are in equilibrium for this curve. One is the ice and the other one is the solution. So P is equal to 2, C is equal to 2, F is equal to C minus P plus 1, F is equal to 2 minus 2 plus 1, F is equal to 1. It is univariant system. It is univariant system. Now along curve OB, OA freezing curve is completed. OB, it is the solubility curve. From O to B, NaCl solution, temperature is increasing. Along this curve, two phases are in equilibrium. Two phases are in equilibrium. Solution phase. One is the solution phase, and the second one is a solution phase, and the other one here, solid NaCl is also there. So NaCl H2O with water. So OA we have seen, these two are in equilibrium. Ice with solution. Here along OB, NaCl in equilibrium with unsaturated solution. Phases to C is 2, F is equal to C minus P plus 1. F is equal to 2 minus 2 plus 1. F is equal to 1. It is univariate. Now, curve BC, although you are increasing the temperature, at the point B, it changes. Here, the solid is formed. At this curve, two phases are in equilibrium. Along BC, temperature is increased. Okay, but the solubility of NaCl will be constant. At point B, NaCl H2O, it starts changing into NaCl solid. Along this curve, it is changing into solid. These two phases are in equilibrium. So P is equal to 2, C is equal to 2, F is equal to C minus P plus 1. So two phases you know, this one and this one. C also H2 and NaCl. So F is equal to 2 minus 2 plus 1. F is equal to 1. Therefore, system is univariant system. The system is univariant system. This curve indicates solubility of NaCl. It is almost constant with increasing temperature. Now, let us go for the point. Eutectic point, cryohydric point, O. At this point, ice, NaCl H2O solution are in equilibrium. P is equal to 3, C is equal to 2, P is equal to 3, C is equal to 2. So F is equal to C minus P plus 1. F is equal to C minus P plus 1. F is equal to C is nothing but 2. Okay, ice, H2O, NaCl. 2 minus 3 plus 1. So F is equal to 0. The system is invariant system. The system is invariant system. And coming to the congruent melting point B, the compound undergoes composition to give solid having incongruent melting point. Here NaCl, the compound undergoes composition to give another solid is nothing but incongruent melting point. So NaCl, it is NaCl H2O, NaCl H2O at 0.15 degrees centigrade. It is giving NaCl. It is so the compound undergoing the composition to give another solid is incongruent system now. So NaCl H2O 0.15 degrees, NaCl and solution. NaCl and the solutions form. At 1.15 degrees centigrade, NaCl changes into NaCl solid. This temperature incongruent temperature. This 0.15 degrees centigrade is incongruent melting point of NaCl. So at this point there are three phases. At point B, the temperature is 0.15 degrees centigrade, incongruent melting point. There are three phases. P is equal to 3. P is equal to 3 phases. 1, 2, 3. At this point, 1, 2, 3 phases. And composition is C, the same. F is equal to C minus P plus 1. F is equal to 2 minus 3 plus 1. F is equal to 0. System is invariant. Areas again I am repeating. Similarly like that of curves, I am explaining areas once again. In the area AOBC, there is only one phase, unsaturated solution phase. On phase is P is equal to 1, but the solution has solid plus, that is NaCl plus water, H2O. C is equal to 2. F is equal to C minus P plus 1. C minus P plus 1. 2 minus 1 plus 1. F is equal to 2. System is bivariant system. The system is bivariant system. So I have revised twice. Along the melting curve AO, the system is univariant. Along OB, solubility curve, system is univariant. Along BC, again the system is univariant. Along the points, the system is invariant. Along the point O and C. Okay. Along the curves, it is univariant. Now, along the curves, you have got univariate. Along the points, we have got that is O point, eutectic point, cryptotic point. It is invariant system. The B incongruent melting point, the system is invariant. Okay, so AO monovariant, OB monovariant, BC monovariant, again BG monovariant you'll be getting. At 2 points, point O, it is invariant system. At point B, it is invariant system. This is eutectic point O. B is incongruent melting point. Here it is invariant systems. Now, in the area, only one area, AOBC above area, it is bivariant system. So, any areas you take, you will be getting the bivariant system. So, using this phase rule, we have calculated the degrees of freedom, that is independent variables, how they are varying for the different phases that are in equilibrium. We have discussed one component system, it is over, two component system, silver lead system, condensed phase system, and congruent melting system, zinc magnesium system, and incongruent melting system, sodium chloride water system. We have seen how the phases are in the equilibrium and how the degrees of freedom independent variables are changing. We have discussed. Okay, I hope everybody have understood the phase rule and the two components, one component system and the two component system, different types we have seen. What are the advantages of this phase rule is it provides a simple method of classifying equilibrium states of a system. This phase rule confirms different systems having same number of degrees of freedom behave in same manner. It is applicable only to macroscopic system and it is not concerned to the molecular structures. It predicts the behavior of the system with changes in variables that govern the systems in equilibrium. So different systems with same variables, how it is changing in their equilibrium can be explained using the phase rule. It also predicts given conditions whether the number of substances taken together will remain in equilibrium as such or they involve in interconversion or elimination of some of them we have seen. It takes no account of the nature of the reactants. That is, the chemical nature is not considered, only the physical nature is considered. The nature of the reactants, the chemical nature is not at all considered for the reactants and products in the phase reactions. The chemical nature of the reactant and products in the phase reactions is not taken into the account. Only the physical nature is taken into the account. So this is the advantage of the phase rule. So I hope you have understood what is the phase rule. Today's class, I have explained you what is the phase rule. Okay, and phase rule, in the phase rule, Gibbs has proposed the phase rule, and general phase rule F plus P is equal to C plus 2. Reduced phase rule F plus P is equal to C plus 1. And the terminology involved phase, component, degrees of freedom. Okay, and in the degrees of freedom, monovariant, bivariant, non-variant systems. And today's class, mainly we have explained about the incongruent melting system. I hope everybody have understood this class, incongruent melting point system of sodium chloride and water. Thank you, everybody.